is the most important part for nowadays AI agent successful. And today, we're very pleased to have Tianxin and Tingwei here to give a presentation about their most recent survey about agentic reasoning. And let me first give a brief introduction about the co-author of that paper. So Tianxin is a final year PhD student at UIUC, and his research
insights in the paper Agentic Reasoning for Large Language Models. The main motivation behind this work is that reasoning in LLMs is no longer just about producing a correct answer from a static prompt. Increasingly, we care about systems that can plan, act, observe, adapt, and collaborate in the dynamic systems. The survey tries to organize the transition systematically. In particular, we frame agentic reasoning through three major dimensions: foundational capability, self-evolving mechanisms, and collective multi-agent reasoning. So let's start the presentation. So let me begin with a brief roadmap. I will first motivate why standard LLM reasoning is insufficient for dynamic environments, and then introduce the core idea of agentic reasoning. After that, I walk through three pillars of the survey, which is foundational, self-involving, and collective agent reasoning. Finally, I will discuss applications, benchmark, and open challenge. LLMs have shown impressive performance on many reasoning tasks, especially in relatively closed settings, such as a math problem or code generation. But this task usually assumes that the entire problem is already specified in the prompt, and that the model only needs to reason internally to produce answer. Real environments are quite different. In the real world, tasks are open-ended, dynamic, and interactive. An agent may need to gather missing information, call tools, revise its plan, recover from failure, and learn from previous attempts. And this is where traditional LLMs struggle. They are good at single-shot conditional generation, but may be weak at goal-directed interaction over time. So the challenge is not only improving reasoning accuracy, it's about enabling reasoning that is grounded in action, feedback, and persistent state. So in this setting, reasoning is coupled with actions taken in an environment. And this slide summarizes a contrast between these two styles of reasoning. So traditional reasoning is largely impulsive. The model receives a prompt, performs a forward pass, and outputs a response. The context here is static, the state is temporal, and the knowledge is fixed at inference time. By contrast, agentic reasoning is interactive and dynamic. Another important change is statefulness. Classic LLMs only rely on the context window, while agents can maintain external memory and persistent state across interactions. So overall, inference becomes a multi-step process rather than a one-shot prediction. Because this area is moving quickly, the field can easily feel fragmented. Different papers focus on different perspectives, such as reasoning, planning, tool using memory, reflection, collaboration, etc. So the purpose of this survey is to provide a unified roadmap, and we organize this literature into three complementary dimensions that capture how agentic reasoning scales from core capabilities to adaptive behavior and finally to collaboration. The first dimension concerns foundational single agent skills. The second concerns how agents evolve over time. And the third concerns how multiple agents reason together. The structure is useful because it separates what an agent can do, how an agent improves, and how intelligence scales across agents. So here I want to briefly summarize the three pillars before diving into each one in detail. For the first pillar, we introduce that supports action, adaptation, and collaboration. To make this more precise, we formalize the environment as a Markov decision process. The environment provides our observations, which may include retrieved documents, tool outputs, search results, and or interaction feedback. The agent then produces actions such as calling a tool, retrieving memory, planning the next step, or reflecting on field examples. Importantly, we also implicitly model reasoning trees, space and a memory or context state. This emphasizes that agent behavior is not only determined by external actions, but also by internal reasoning dynamics. The key conceptual point is that agent behavior emerges from the synergy between reasoning and acting. Reasoning happens internally, often in latent or textual spaces, while action changes with the external environment. This view helps unify many agent frameworks under a common perspective. A second important distinction in the survey is between in-context reasoning and post-training reasoning. In-context reasoning improves behavior at test time without changing model parameters. This includes approaches like chain of thought prompting, search over reasoning trajectories, tool using, or retrieval-driven adaptation. The model stays fixed, but the reasoning process becomes more structured and complicated. And post-training reasoning, in contrast, changes the model parameters. This includes supervised fine-tuning on reasoning traces, reinforcement learning over the trajectories, or training on action sequences. So one way to think about it is this: in-context methods improve behavior through runtime, and while post-training methods improve behavior through training capability. And this distinction will appear repeatedly through the three pillars. So now that I have introduced overall framing, let me move into the first pillar, foundational agentic reasoning. The first pillar asks a simple but fundamental question: what core capabilities does an individual agent need in order to act intelligently? Our answer is that three components are especially central. First, the agent must be able to plan, meaning it can decompose the goal into manageable sub-steps. Second, it must be able to use tools, extending its capabilities beyond pure language generation. Third, it must be able to search, meaning it can retrieve and navigate external information dynamically rather than relying only on the parametric knowledge. Together, these capabilities form the minimum operational basis of agentic reasoning. And planning is perhaps the most intuitive agentic capability. When a task is complicated, an agent should not attempt to solve everything in one step. Instead, it should decompose the task, decide what to do first, and maintain some structure over the decision process. At inference time, this often takes the form of workflow design, tree search, or hierarchical reasoning. Frameworks like React and Train of Thought are examples of this style. And at the post-training level, planning can be internalized through reward design or optimization over long horizon trajectories. The larger point is that planning introduces foresight. It allows the agent to reason not only about the current state, but also about the sequence of future actions. And planning methods can be organized along two axes. The first one is structure. Some planning methods are sequential, where the agent proceeds step by step. Others are tree-based or graph-based, where multiple reasoning paths are explored. Still others can be hierarchical, where high-level goals are decomposed into sub-goals and subtasks. The second axis is format. Plans may be expressed in natural language, symbolic language, executable code, or even visual or multimodal representations. This taxonomy is useful because it separates how a plan is organized from how it is represented. A method may be point to the fourth point, and it is expressed in natural language. And for the second figure, the plan can also be expressed in a symbolic way by decomposing the task into several steps one by one. And it can be also expressed in coding, where the code will be executed to achieve the task. And we can also extend the in-context learning to the post-training to better internalize the knowledge. Yeah, what unifies them is the idea that better task performance often depends on reasoning about structure before execution. In other words, planning is not just about generating intermediate text, it's about introducing decision structure that improves action quality over time. Yeah, the next capability is tool using. It's a mechanism that most clearly extends LLM beyond the closed word. A traditional model can only reason over what is already in its parameter and prompt. A tool using agent, by contrast, can call calculators, APIs, databases, simulators, search engines, or executors. This changes the nature of reasoning. The model is no longer reasoning over tokens, it's reasoning over possible actions and their consequences. And that's why we describe this shift as moving from a chain of thought to a chain of actions. The reasoning process now includes deciding when to act, which tool to use, and how to interpret the return result. And this makes the system more grounded, more precise, and more adaptable. Tool use can also be categorized into different forms. One distinction is between in-context integration, where tool calling is orchestrated at inference time through prompting or runtime control, and post-training integration, where the model is trained to use tools more reliably. Another form is orchestration-based systems, where an external controller or framework manages a collection of tools, and it will route the different tasks among different tools. These distinctions matter because they correspond to different system designs. Sometimes the model itself chooses the tool, sometimes an outer framework manages that process. In either case, the core goal is the same: to make reasoning actionable and grounded in external resources. Yeah, here we also introduce several of our recent works about process reward modeling, or PRM, which is important because it provides supervision at the level of intermediate reasoning steps, as we mentioned, rather than only as a final answer. And this is especially relevant to agentic systems, since many agent failures happen in the middle of a trajectory. An agent may plan incorrectly, retrieve the wrong evidence, or misuse the tool, even if the final output looks superficially plausible. PRMs offer a kind of third-person perspective on reasoning. Instead of only asking whether the final answer is right, they ask whether the process is sound. And this makes them useful for taxon scaling, verification, ranking, and trajectory selection. So PRMs can be seen as an enabling technology for more reliable agentic reasoning. Here, the distinction between discriminative and generative PRMs become important. Discriminative PRMs learn to score steps or trajectories, often using binary or scalar labels. Generative PRMs instead produce rationales, critiques, or judgment in natural language. For agents, both variants are useful. A discriminative PRM can provide lightweight trajectory scoring, while a generative PRM can explain what went wrong and guide revision. This matters even more in tool using setting, where correctness may depend on sequences of actions rather than only on text quality. So precise supervision becomes a natural complement to action-based reasoning. And if you are interested in this setting, you can check these two papers of our group. Yeah, next, let's introduce the third foundational capability, which is search. Driven process rather than a static query retrieve process. And this is especially useful when the task is open-ended, ambiguous, or requires multiple hops across documents or modalities. So search becomes part of reasoning, not just a support module. Such methods can be roughly organized into these different categories. Some methods focus on in-context agentic search with the model performs search iteratively during inference. Others focus on post-training agentic search, where the model is optimized to search more efficiently. A third category introduces structure-enhanced search, where reasoning chains or topologies explicitly guide retrieval. This taxonomy is useful because it reveals that search is not just about better ranking, it's about coupling retrieval with reasoning and decision making. So once again, the key theme is that agentic systems integrate computation and interaction rather than treating them separately. Here I list several relevant papers, and more, you can find more papers in our survey. Yeah, for this taxonomy, I want to highlight our recent paper, which is accepted at Clear 2026 as an oral presentation. The motivation is that why search becomes particularly challenging in multimodal and dynamic environments. Queries are often very ambiguous and they're specified or dependent on multiple pieces of evidence. In multimodal settings, the agent may need to connect text, image, retrieve documents, and temporal information. These tasks demand richer and more fine-grained reasoning behaviors, such as iterative decomposition, cross-modal retrieval, and evidence integration. A simple retrieval then generate pipeline is often not enough. The agent needs to reason about how the search itself should proceed. And this is why structured reasoning becomes essential in agentic search environment. And we also combine our proposed benchmark with the previous ones, you can see that most dataset only have a 1 to 2 hop retrieval chain, and the retrieval process is fixed with a retrieve then generate process, and there is no stepwise annotations, no reasoning topology modeling. So that's the gap we want to fill. So MC search is introduced here as a benchmark for multimodal agentic search with long structured reasoning chains. The important point is that this benchmark goes beyond short fixed retrieval tasks. It includes multiple reasoning hops, explicit topologies, and stepwise annotation. This makes it possible to evaluate not only whether the final answer is correct, but whether the agent searched and reasoned in the right way along the trajectory. So benchmarks like this are important because they align evaluation and how agentic systems actually operate. They let us study process quality, not just endpoint accuracy. In the table, I show the statistics of the benchmark. In this data set, we have 5 reasoning topology, which is image initiated chain, multi-image forks, text initiated chain, parallel image text fork, and text only chain. And for more details, you can check out our paper in MC search. Another important methodology point we studied is that if we only evaluate the final answer, we miss very serious reasoning failures. An agent could retrieve irrelevant evidence or search unnecessarily or follow a poor plan, yet still land on the correct answer by chance. So, and that's why we need process level metrics such as hit per step and rollout deviation. These metrics capture how closely the actual trajectory matches the intended reasoning chain. And our benchmark provides a platform to evaluate and enhance that. We also provide an agentic evaluation pipeline, which incorporates multimodal reasoning chain for structured evaluation, search line, which train on our dataset to consistently improve on the agentic performance. Yeah, so that completes the first pillar. So far, we have focused on the core operational capability that allow a single agent to function. Now I want to move to the second pillar, which asks a different question. Once an agent can act, how does it improve over time? This pillar is about adaptation through experience. A static agent may solve a task, but a self-evolving agent improves from task to task and from interaction to interaction. In this survey, we emphasize two central mechanisms behind its evolution, which is feedback and memory. Feedback tells the agent what worked or what failed. Memory lets the agent retain and problem solver into a learning system. And there are several major forms of feedback in agentic systems. One is reflective feedback, where the agent critiques its own reasoning during inference and revises the result. Another is parametric adaptation, where feedback is incorporated through fine-tuning or reinforcement learning. Third is validator-driven feedback, where external systems such as compilers, tests, or simulator provide pass or fail signals. These mechanisms differ in how feedback is generated and how it's used, but they all support iterative improvement. The key idea is that agents should not rely on one-shot generation. They should be able to inspect outcomes and revise behavior. And this slide reframes feedback from another perspective in terms of reward sources. Rewards can come from the environment, from programmatic rules, from models, or from human. For example, embodied agents may receive simulator rewards, coding agents may use unit tests, language agents may rely on model jobs, and alignment system may use human preference data. The reason reward design matters so much is that it defines what kind of improvement the agent is encouraged to make. If the reward only measures final outcome, the agent may learn shallow shortcuts. The reward is more precise whereas the agent with the better reasoning behavior. So reward it's not just a training signal, it shapes what kind of agent emerges. And designing reward in the agent system is very important and emerging area. And the memory is a second core mechanism in self-evolving systems. Without memory, every interaction is isolated. The agent can't accumulate knowledge, remember previous failures, or adapt to user-specific preferences and histories. In this survey, we organize memory into three parallel dimensions. The first is in-context use, which includes conversation memory and short-term experience within the context window. The second is structured representation, such as graph memory or multimodal memory. The third one is post-training control, where the agents learns what to store, update, or forget. This framing is helpful because memory is not only about storage, it's about how to represent and how to control. A good memory system supports both recall and decision making. Yeah, from another perspective, we can also decompose the memory system into user memory and agent memory. This slide focuses on our recent user-facing memory, especially for conversation or assistant settings. In real-world interactions, user information is multi-session, evolving on and often multimodal. A capable assistant should remember relevant facts, resolve conflict, and adapt to changing preferences. This goes beyond standard long context QA. It requires persistent memory across sessions and often across modalities. So personal memory is not simply a retrieval problem, it's a dynamic knowledge management problem embedded in the interactions. Here we introduce a memory gallery as a benchmark for multimodal long-term conversational memory. The key value of this benchmark is that it combines multi-session interactions with non-trivial multimodal dependencies. That makes it more realistic than text-only or single-session benchmarks. It also evaluates multiple memory abilities, including extraction, adaptation, reasoning, and knowledge management. This is important because memory quality is not only about factual recall, it also includes temporal reasoning, entity tracking, conflict detection, and even refusing to answer when memory is uncertain or um, inconsistent. So memory gallery broadens what we mean by evaluating agent memory. So why the benchmark improves upon prior ones compared to the previous data sets? It provides more useful visual information, more realistic long-term interaction structure, and more unified evaluation pipeline. This matters because many previous memory benchmarks capture only part of the problem. Some focus on text-only recall, where others focus on short-term multimodal understanding. Mem gallery better reflects the combination of persistence, multimodality, and evolving context that real assistance must handle. So it serves as a stronger testbed for long-term memory in agents. For more details, you can check out the paper if you are interested. Yeah, another perspective is from personal memory to agent memory, or we can call it experience. Solved a similar task before, discovered a useful workflow, or learned from a field experience. That experience should be reusable. Experience memory therefore supports generalization across tasks, not just recall within a conversation. And this is a crucial step toward agents that can improve over time. This slide formalizes the experience memory settings through streaming tasks rather than evaluating a task independently. We consider tasks arriving continuously over time. Some tasks may be single-turn reasoning problems, while others may be multi-turn interaction problems. The challenge is that the agent must learn across tasks at test time. It can't assume a clean reset after each episode. This makes memory an active component because past experience can influence current decisions. So the problem becomes one of continual adaptation during deployment. Here we present remem as a framework where memory itself becomes a reasoning object. Instead of treating memory as a passive database, the agent actively thinks, acts, and refines memory during inference. This means memory can be reorganized, pruned, or updated as a part of the reasoning loop. This makes memory as a first-class mechanism in self-evolving reasoning rather than just an auxiliary database. Yeah, beyond using the feedback in the memory, there are many applications of self-evolving. The agent may develop new capabilities during test time. For example, they may synthesize planning tasks for themselves, create new tools when there is a need, refine memory bases when there are conflicts, or improve such strategies dynamically. This introduces the idea that agents are not only solving tasks more effectively, they may also be expanding the set of skills available to them. And that's why self-involving reasoning is broader than reflection. It includes probability growth. Here I collect several examples of that broader evolution. Sorry. Some approaches focus on evolving skills directly. Others focus on tool development and synthesis, where agents create or refine tools that later support future reasoning. Still others involve co-evolution of data and the models, where the agent helps generate the training signal that further improves itself. Taken together, these directions point toward a more autonomous learning loop. Instead of waiting for human design data or training pipeline, the agent increasingly participates in creating the structure that enable its own improvement. Yeah, if you are interested, you can check all these papers or look at our survey. Yes, final step is to ask what happens when reasoning is no longer confined to one agent. This brings us to the third pillar, collective multi-agent reasoning. It starts reasoning distributed across multiple agents. The key intuition is that a single model does not necessarily need to do anything. Different agents can assume complementary roles such as manager or worker, critic, or verifier. This creates opportunity for specialization, division of cognitive labor, and more robust collaboration. Collective reasoning, therefore, extends agentic reasoning from individual capability or to organizational intelligence. It's not just about having many copies of the same model. It's about coordinating different functions within a system. This slide highlights three core questions in multi-agent systems. First, how should roles be assigned? Should roles be fixed or should they adapt to the task? Second, how should agents collaborate? They need communication protocols, negotiation mechanisms, and ways to exchange intermediate reasoning efficiently. Third, how should the group co-evolve over time? Should the shared state and the memory become important for long-term coordination and adaptation? So multi-agent reasoning is more about structured coordination. Yeah, a useful way to think about multi-agent system is through role taxonomy. Many systems naturally resemble organizations. One agent sets objectives, another executes subtasks, another critiques outputs, and another maintains shared state. The role decomposition reduces checks and balances. It allows one agent to compensate for another's weakness and can improve reliability. For example, in software engineer, we may want planner, coder, tester, and reviewer roles. In healthcare, roles may correspond to structure of the domain they operate in. And that's one reason they are so flexible. Specialization can be tailored to the task itself. This slide contrasts in-context collaboration and post-training collaboration. In the first one, the system uses a predefined or runtime generated communication structure without updating parameters. This includes manually crafted pipelines or LLM-driven pipelines. In post-training collaboration, the collaboration structure itself may be optimized through prompt tuning, topology search, or learning-based routing. So once again, we see the same broader pattern as earlier in the talk. One family of methods improve behavior through runtime structure, and another family improves it through training. This parallel between single and multi-agent design is conceptually important. Memories here becomes even more complex in this setting. It organizes multi-agent memory along 4 dimensions: architecture, content, topology, and management. Architecture asks whether memory is hierarchy or flat. Content asks whether memory stores semantic or procedural memory. Topology asks whether the memory is centralized or decentralized. And the management asks how memory is summarized, filtered, verified, or forgotten. And it can be more complicated in the real-world system. These design choices significantly affect coordination, quality, scalability, and consistency. So memory in multi-agent system is not a minor implementation detail, it's a structural component of collaboration. And this slide pushes the multi-agent story further by emphasizing evolution over time. Rather than hand-designed or coordination rules, we want systems that adapt their structure. And this introduces a question like how roles should emerge, how communication protocols should stabilize, and how collective behavior should be aligned with human goals. And this is where multi-agent reinforcement learning or alignment and co-evolution all become relevant and important. I provide some examples of our recent works across 3 subthemes: context inference, collective memory, and collective training. The common pattern is that multiple agents are combined to reduce uncertainty, maintain long-term context, or improve reasoning through coordinated optimization. Yeah, to save time, I won't go into the details of every paper. If you are interested, you can check out this paper or look at our survey. Yeah, I think that's all for the master part of our survey. Next team, we will go through the applications and the benchmarks.
Yeah. Let me share the screen. Yeah. So yeah, thank you, Dawi, for the introduction, and Tianxin for going through all the 3 layers. So foundational, self-evolving, and also the collective multi-agent layers. And in this application benchmarks, well, basically I will show you some examples, and especially like very frontier research, like how these 3 dimensions or how these 3 layers are used in recent applications for agentic reasoning. So in our paper, basically we study 5 specific applications. So the first one is the mathematical and coding agents, and the second is scientific discoveries, and then embodied agents, healthcare, and autonomous research. Yeah, so the overview here, you can see like how these different layers spanning from foundational, so including the planning capability, how to use tool, and then how to use search tools and retrieval. And then in the second layers, there's some feedback loop and also like different memory mechanisms or evolving strategy. And the final layer is about how different agents collaborate and how they co-evolve. And I will only go through a few examples, specifically on the mathematical scientific discovery and then the research agents. So one paper I would like to share with you is this is from the C team from Python's. So it's basically a theorem proving agents. And what I want to show you is like how these frontier agents actually have capabilities that fall into our three categories. So for example, in this paper, there's for example, the agent can do code execution for the Lin, which is one of the formal mathematical language. Into and also this paper also shows the agents introduced in the paper can use a certain library called mathlib, and then during the proving procedure you can do search and retrieval from this library, which is also some specific capability under a tool use layer. And then we can also have like several different type of verification process to verify whether the lemma or theorem you generated from the agent is true or false. And this can be some feedback signals and going back to the agent, and then the agent can act based on these feedback. And then there's also memory mechanisms. So for example, the lemma that is verified through this feedback this verification layer can be stored and then be reused in future. And also there's obviously there's a multi-agent framework. You can see there's a different provers or a model that sketching proofs, and also the agent that proves the lemmas. So there's like different type of agents that can work together to prove a specific mathematical theorem. And for scientific discovery, this is also a very recent papers archive. So I choose to share these papers because they also include a lot of the agentic reasoning capabilities that we share and we discussed by Tianxin previously. So you can also see that basically the agentic capability introduced in this paper, there's code execution to run experiments or to verify something, which is also falls under the tool use layer. And then there's also search and retrieval modules that can search the data online and also the literature or books. This is also some kind of tool use capability. And then they also introduce certain type of memory module that you can have some drafts or some partial ideas that can be reused, and these will be stored in a certain memory module. And then there's also feedback loops that basically when your ideas or the analysis going on, you can always have some language based feedback, and it can be inserted back to the agents that to produce better results. And then you can also see that in this figure, there's different, basically also a multi-agent collaboration framework. There's a ideation agent that generate ideas, and then there's the analysis agent to analyze the ideas or the codes there's basically from the ideation agent and also the experiments agents, and there will be a lot of intermediate reports or code base that can be stored as memory. And then there's a critic agent that can produce certain type of feedback, and then the ideation can be can base on or the condition on the criticized results to further improve itself. And also there's another interesting topic in scientific discovery, which is basically trying to solve very difficult scientific problems. So these problems are mostly open problems that are also studied by humans as well. So like, for example, optimization constants in mathematics. So I think this line kind of starts by the alpha involved, and there's several representative follow-up works like TDD discovery or delta evolve. And specifically in this setting, the agentic capability is also included, and definitely. And there's interestingly, there's like a program database, and that is also something like a memory mechanism that is used in this system. And then interestingly, there's a test time training or learning module for post-training the base agents. So for example, if you have certain programs or theorems that is verified, and those things can be served as like additional data that can be used to train like the base model. So for example, in this data evolve papers, the prompt it will generate a batch of the prompts, and then it will go through the verification states, and then the results can be used to further fine-tune using reinforcement learning to fine-tune the base model to further improve itself, and then it can actually achieve like a performance with much larger models. And also for another category is called the embodied agent. So actually in this category, the capability is actually very natural. We will have to interact with the environment. And specifically in this setting, we also have observe the world scenario, and they have to based on the observation and then take actions. So this is also kind of like a tool use capability. And then because they have to interact with the environment and then do execute actions, so these will definitely be another example of tool use capability. And then all the user profiles or the entities that is experienced by the agent can all be stored as a memory. And another special things to consider in embodied agent recently is to integrate with the so-called world models. And then instead of basically these world models can inherently tell us how to sense or how to see this world and how to predict the next state. And then also there's mental world models that basically tell us, for example, how other agents think and act in the same environment, and how can we adjust our mental state based on the observation or based on our understanding of how other agents thought. And also this is another category of application, which is autonomous research. And you can see that there's also a bunch of papers starting from like AI scientists V2 or AI researchers. So these papers are trying to produce papers that look like academic publication. So something like academic format papers. But now actually people are trying to have something beyond this. So they don't want only producing papers that are seemingly good, but they're trying to produce knowledge or try to create knowledge, like try to expand the frontier of knowledge. So also very similar to the goal of scientific discovery in some sense. So this is also a very recent news. So this is called the FARS, fully automated research system. It's from the Ananuma company that they launched YouTube live stream running for days, and then they produce like tens or hundreds of papers. Basically, they have an entire scalable automated pipeline. So you can see from the right-hand figure. So they also have certain type of ideation agent, planning agents, and also agents that do experiments or do paper writing. And they also have, for example, the memory layer. So they have a shared file system that whenever you have some experiment run and also some kind of idea or intermediate results, it can be stored into these file systems, and you can see there's folders storing references of literature or different latex form, latex code, or even like markdown files. And then you can also interact with large models and also do search and retrieval from web resources to basically augment the ideation agents. So you can also see there's a lot of 3 layers of capabilities within this framework. Yeah, so these are some like some interesting things for the application. And then for the benchmarks, we also kind of categorize in our surveying, we'll categorize into 2 types of benchmark data sets. The first one is to evaluate the core mechanism. So basically, trying to evaluate the model's ability. For example, for tool use or how you do memory management, and also test about how the agent can collaborate with each else. And the other category is called the application level. So basically, these benchmarks are application specific, which is like largely tied with the previous section, which is application section. That these benchmarks are trying to probe the agent's capability to do something within a specific domain. And some of the interesting future work that we can do is that how can we go beyond just only evaluating the final answer accuracy, and also trying to see how the reasoning process quality matters. And also there's a need of how we can develop some data sets that actually represent like a real world scenario, that we're not only looking at a certain type of task, but we actually have a shifting or like a continually changing environment that actually the task distribution is changing. Yeah, so also we also list a few open challenges in our survey paper. So yeah, due to the time, probably I will just briefly go over them. So for example, the first one is that how can we do user-centric personalization? And this will be very related to the memory mechanism, because when you do some conversation with your, let's say, GPT models, then potentially this model have to remember and recall some of your personal preferences. So this can it's fixed. Then you have to bring something efficiency and potentially even better efficacy. And the final part is more about the trustworthy. So basically, we know how there's a lot of safety issues, like coding agents or even like OpenClaw. So there's many agents that is very capable, but you have to grant them certain type of access, and they'll probably use your computer to do something not that good. So to prevent misuse or to establish accountability, the governance and the safety aspect is also very important for future agentic reasoning research. Yeah, so this marks as our final slide, I guess. So basically, we try to conclude this as this survey paper as a paradigm shift from the four aspects that we consider in the paper. So we do a conceptual framing. So we have these three layers that is introduced by Tianxin, and also we observe these things in the application sections a lot. And multiple domains, they will share similar type of agentic capabilities. So across foundational, evolving, and collective layers. And we also have some systematic review on categorizing agents and these agentic reasoning papers into single agent, or multi-agent systems, and also like whether you train your model or not train your model, like in context learning and post-training dimensions. And we also include like a very comprehensive review on the application and the evaluation benchmarks. And we also provide some open challenge as the final chapter in the survey paper. So yeah, that should be the end of our talk.
Yeah, thanks Tianxin and Tingwei for this very interesting introduction. And I personally learned a lot from the talk. Basically, for example, some similar concept like reasoning and planning, and also from the paper you mentioned about self-evolving. And here I think it's our Q&A session, and for our audience, just feel free to share any of your questions about the paper or about the topic we introduced today. And maybe I can first ask a question about the self-evolving part. I think it's a very interesting part because I also work on this. And recently, I mentioned I noticed a paper about mis-evolving, which means, for example, if we just let an agent to self-evolve in an environment, right? Maybe sometimes it will just show some behavior that we don't want it to learn. So I think it's also similar from, for example, model collapse that we want, for example, the backbone model to self-improve. Maybe there will be some bias to be accumulated. And finally, we just produce a model that is not good enough or maybe not enough to produce even regular context. Yeah, so here my question is, do you guys think this mis-evolving problem is a reward problem that would have some negative impact in real-world scenario, or we still don't give agent this kind of permission to have this mis-evolving?
Yeah, I can share a little bit. So thank you for your question. So I feel I'm also personally working on this kind of self-evolving, self-improving agent. So I think I think this is a real problem because we all know that there's a data scarcity problem, that most of the data is kind of used by pre-training, and we already kind of use up all the web data or at least public data on the internet to train our model. So I feel this kind of self-improving or self-evolving is definitely something that we have to let our agent do in the future. And then one of the important things, just as you said, example, like get data that's and I personally also have some ongoing projects that basically saying that these generated data from yourself or from similar capability models has to be selected and has to be filtered a lot to make sure your model can actually learn, especially when you have a dynamic environment and you are learning from experience. So I don't know whether I answer your question, but I feel this is a real problem, and we definitely have to devote like more effort in this this field, because the data is kind of in future the agent has to kind of create their own data, and then they have to use the right data to train themselves.
I see. Yeah, I think it's very clear. Yeah, and I also agree that, for example, previously maybe we have the full control about what agent can learn, right? When we use some traditional way to train it. But now when we have self-evolving agent, maybe they have the accountability or the full access about what they want to learn in a more open-ended scenario, for example, the web or some simulated environment. I think that should be a real world problem. Yeah. And I think it would be a very interesting one to do some research. Yeah. And oh, we have a question from our audience. It's about because in the survey we introduced two ways to build this self-evolving agent. One is in-context learning, and another one is basically parameter updating. Right? So the question is about which way might be more promising in the future for self-evolving agent building.
Attention, do you want to take?
Yeah, maybe I can comment a little bit. I think it depends on the tasks we are handling. In some cases, for example, in the personal scenarios, we're unable to collect the data, and because of the privacy issues. So the only possible way we can do is to evolve our context to non-parametric adaptation. Yeah, because of the data issues. But I think in general, doing parametric adaptation is more effective and a more general solution to address the problem.
Yeah, I agree. I think it depends. And yeah, and we have another question about OpenCloud, which is very, I believe, popular nowadays. So I think the audience just wants to know your guys' opinion about OpenCloud. So because basically do you think it's something representative about the second half of Agentic?
Yeah, I think sure, it's a representative case of the second half in the AI agents, and it's a very successful business example here. But I think OpenCloud do exhibit and reveal many safety issues. For example, in last month, I don't know if you read the news. One Meta director is connecting OpenCloud to his personal mail inbox. Yeah, but she can't control the OpenCloud, and it just continued to delete the emails, and she has to shut down the server to stop the OpenCloud. And recently, I also see that there is another follow-up work named IronClaw. Yeah, it's proposed to solve the safety issues in the OpenClaw.
I see.
Yeah, I think if we can address the issues, OpenClaw can be a very powerful and useful tool in our daily and working scenarios.
I agree. Yeah, I think when we use OpenClaw, some kind of very powerful tool, we also need to be aware of the safety and security problem. And that might also be a very promising direction for me, maybe to do some research on.
Yeah, I totally agree.
Yeah. All right. I think we don't have any other question from our audience. And thanks again to Tianxin and Tingwei for the interesting talk. And yeah, let's talk about today's talk. Thanks.
Yeah, thank you very much.
Yeah, thank you very much for the invitation. Thank you for attending our talk.